Today we're going to look at surface area and volume of pyramids and cones. So a pyramid is a polyhedron where the base is a polygon and the lateral faces are triangles, which really means that we can either have a square base, a rectangular base, a triangular base. We've got some sort of polygon, meaning no curves, as our base, and all of the other surfaces are triangles. So the vertex is the common vertex at the top where all of those lateral faces meet, and the slant height is the height of the triangle, but as it's shown here, because this triangle is tipped over a bit, if you will, it looks slanted. So we're going to refer to that as the slant height. So with that, you may notice on your formula sheet that you've got the surface area formula as the area of the base plus half the perimeter times the slant height. So that cursive L stands for slant height. Down at the bottom, we also have the volume formula of a pyramid, 1/3 the area of the base times the height. Now with that, anytime that we have a polyhedron that comes to a point at the top, so we've got either a pyramid or a cone, we are always going to have 1/3 of the general volume formula. Because yesterday we learned that volume is typically the area of the base times the height. But if we come to a point at the top, we now have 1/3 the area of the base times the height. And this is a little bit hard to visualize, but if you can imagine taking this shape right here and inverting it upside down, so that we have two more of them that would fit right here and right here. What we're essentially saying with that 1/3 is that this pyramid is 1/3 the size of a prism with the same base. So like I said, it's a little bit hard to visualize, but if you can imagine inverting that pyramid, creating a duplicate of that, and squishing it all together, we would create a prism of exactly the same base size. So with that, we're going to find the lateral area, surface area, and volume. So going from here, my lateral area, remember that that's all of the surfaces that are not the bases. In this case, we only have that one base that's on the bottom. We have that hexagon. So our lateral surfaces are the triangles. And since this is a hexagonal base, meaning we have a hexagon on the bottom, I know that I have 6 triangles as my lateral area. Now the good thing about this, because this is a regular hexagon, that means that all 6 of those triangles are the same size. So if I look at one of them, if I try to look at this guy here, that is a triangle with a base of 10, because it's a regular figure, so all of the bases here are 10, and a height of 14. So the area of that can be found by taking 1/2 the base times the height. And I can multiply all of that together by 6, since there are 6 of those triangles. So 6 times 1/2 times 10 times 14 gives us a lateral area of 420 square feet. For surface area, we're going to take those 6 triangles plus the area of the base, right? So now we're going to add in this piece that we forgot. So I'm going to take what I just found plus the area of a regular hexagon. And to find the area of a regular hexagon, that's that 1/2 apothem times perimeter formula. So looking at my picture here, what's really nice is they did give me the apothem. They told me that that was 5 square roots of 3 from the center out to the outer edge. And the perimeter of this shape, we've got 10 6 times, so we've got 60 feet as our perimeter. So now, all I have to do is type all of that in my calculator. It doesn't say I have to leave it in simplest radical form, thankfully. So I'm just going to type every bit into that into my calculator and round to approximately 679.8 square feet. Last but not least, they also want us to find the volume. So for volume, remember when we come to a point at the top, that's 1/3 the area of the base times the height. So I've got 1/3 of the area of that hexagon, which again, we talked about right here, was that 1/2 apothem times perimeter. So I'm going to plug that information in. And then my height is the vertical height of this figure. So I've got to find from the center straight up. Now at this point, I don't have that information. So I'm going to have to come off to the side and figure out how tall is this figure. So looking at what I know that I have 5 square roots of 3 here. I know that the slanted height is 14. And because that point should be directly above the center, I know that there's a right angle here. So I'm going to redraw this right triangle where I have 14, 5 square roots of 3, and an unknown vertical height. And I'm going to use Pythagorean theorem to figure out that height. So 5 square roots of 3 all squared plus the height squared equals 14 squared. So at this point, be very careful. When you type 5 square roots of 3 all squared, make sure you put all of that in parentheses. So that is 75. 14 squared is 196. And I left off my squared here, so I'm going to double back to fix that. So 196 minus 75 is 121. So the square root of 121 tells me the height of this figure is 11. So with that, I'm going to come back over here and plug in 11 for the height of this figure. At this point, this is all a calculator problem, so 1/3 of 1/2 times 5 square roots of 3 times 60 times 11. And that gives me an approximate volume of about 952.6 cubic feet. So remember guys, with volume, we're talking about how much space is inside of something. So if we were to fill this shape with water, we would need 952.6 cubic feet of water. Whereas when we're talking about area, we're talking about the space on the outside of the figure. So we're imagining either painting the outside or wrapping the outside, some sort of component that only deals with the outside of the figure. So now that we've done a tough one, we're going to do a couple of easier ones here, hopefully for us. We're going to find lateral area, surface area, and volume. So remember, lateral area is all of your surfaces except for the base. So in this case, we have 4 triangles. And for the purposes of this class, we're only going to look at regular pyramids, meaning we're going to focus on what the dimensions are of that component based on if it's regular, this is also 2. So with that, looking at that triangle, I've got a height here of 3 for the triangle, I've got a base of 2. So with 4 triangles, I've got 4 1/2 base times heights, or 4 times 1/2 times 2 times 3. And I'm going to multiply all of that together and see what I get. And I should end up with 12 square feet for the lateral area. For surface area, we're going to take those 4 triangles plus the base. So we're going to take 12 plus the area of the base, that's a 2 by 2, so that's 4, so that's 16 square feet for surface area. For volume, anytime we come to a peak at the top, we're going to do 1/3 the area of the base times the height. So 1/3 of 4 times our vertical height. Again, your vertical height comes from the center of the figure straight up. So we don't have that information here. But again, I can form a right triangle where I've got x squared, or the height squared, plus 2 squared would equal 3 squared. So I really have 9 minus 4, which is 5. So x squared equals 5, which means this is the square root of 5. And rather than rounding that, I'm just going to bring that information here, and then I'll round everything at the end. So 1/3 of 4 times the square root of 5 tells me that my volume is approximately 3 cubic feet. Again, guys, we've got 2 other examples here. Number 7 is going to be very, very similar to the one that we did before. So I would recommend that you try 7 on your own and look back to that first example if you need to. But we are, for sake of time, going to skip number 8. So let's talk about cones for a minute. So a cone has a circular base and comes to a peak at the top, or a vertex at the top. For the purposes of this class, we are only going to talk about what's called right cones, which means from the center straight up will always form a right angle. We're not going to talk about if they're slanted or what we call oblique. But with that, our formula here, because it comes to a point at the top, our volume formula is still going to be that generic 1/3 area of the base times the height. However, since the base is a circle, to find the area of a circle, we use pi r squared. So you'll notice on your formula sheet that you see that equation for volume. For surface area and lateral area, we've got to kind of think through these different components. Now this is going to be a little bit hard to visualize for those of you who are not here in person. However, if you can imagine, if we took scissors and cut along this edge so that we could unravel that cone, it's kind of going to have a fan shape to it. We're going to talk about how do we handle that component. So again, we've already talked about where the volume formula came from, but let's look at the surface area. So the surface area says take the area of your base plus 1/2 the circumference times the slant height. So what you're actually doing is you're figuring out each of these different pieces. If we unravel that fan, if you will, we're treating it as if there are a bunch of tiny, tiny triangles around the outer edge of that circle. So our generic formula of a triangle is 1/2 base times height. So if you'll notice, the base of that triangle would be the circumference formula, right? Because we've got a curved surface there. So 1/2 of 2 pi r times the slanted height, right? We're not talking about the vertical height of this figure. We're talking about that tipped over height, which kind of looks like a cursive L. So what we're going to do here, if we simplify that, 1/2 of 2 is just 1. So you'll notice on your formula you only have pi r slant height as the last component of this formula. So let's look at what we have. So our surface area is what we're looking for here. So for surface area, we have that fan shape, if you will, plus the circle on the bottom. So remember, for the fan shape, we're going to use 1/2 the circumference times the height, or the slanted height. So I'm going to change that to that cursive L to mean the slanted height, plus pi r squared. So breaking that down, 1/2 of 2 is just 1, so we're going to rewrite this as pi r slant height plus pi r squared. Now in this case, they could ask you to leave this in terms of pi, which in fact they do. So when we look at this, I'm going to be very careful to carry pi along with me till the very end. I notice that I don't currently know this slanted height. However, I do have a 3, 4, 5 triangle in disguise, so I can find that slant height pretty quick. If I didn't recognize that though, I could use Pythagorean theorem. 6 squared plus what squared, in this case that's 8 squared, equals what squared. Either way, we should end up with 10. So pi times my radius times the slant height plus pi times my radius squared. So in the front here, I have 60 pi, and on the back end, I have 36 pi. So 60 and 36 added together give me 96 pi square meters. Again, for volume, anytime we have a peak at the top, we're going to put 1/3 the area of the base times the height. Since the base is a circle, that's 1/3 of pi r squared times the height. So with that in mind, we've got 1/3 of pi times 6 squared times my vertical height straight from the center, which is 8. And again, if I'm leaving this in terms of pi, I'm not going to type pi in my calculator, but I'm going to type all of the other components, and I end up with 96 pi meters cubed. Now you'll notice in this case the volume and the surface area come out to be the same number, but they do have different units, so they're representing different components of this figure. That is going to happen from time to time. It'll be rare, but if that happens, it's not a direct indicator that something has gone wrong. That is just meaning it's a coincidence. So you've got a couple of examples of cones here that you may want to try. For sake of time, I'm going to move us forward just a little bit, but I would recommend that out of these three, you at least try one of them. And also notice on number 12, they give you the diameter, so make sure before you plug into any formulas, you find that radius. So this last little bit here, we're finding the volume of the solid. So we're not concerned about the surface area, we're just concerned about the volume. So I'm kind of going to talk us through a couple of these. We're not going to solve all of these together, but we are going to talk about how would we approach this. So remember that volume means how much space is inside of something. So for number 20, I would need to find the volume of the cylinder plus the volume of the cone, because I've stacked one on top of the other. Same thing for number 23. I would need to find the volume of the pyramid on top and the volume of the pyramid on the bottom. But since they're the same, I could also think of that as double the volume of the pyramid, or I could think of it as one pyramid plus the other. Again, since they're congruent, either way will work. For the ones in the middle, we have a shape cut out. So for number 21, I would need to find the volume of the cube. Again, that's a cube whenever all of the dimensions are the same, minus the volume of the pyramid that has been removed from it. For 24, I also have a cube, so I would need to find the volume of the cube minus the volume of the cone. Similarly, on 22 and 25, on 22 I would be adding together, and on 25 I would be subtracting. So be careful with these types of questions. Make sure that you're following each of those formulas carefully. You're subtracting when you need to subtract and adding when you need to add. Also, your directions here do tell you to round to 2 decimal places. We normally round to the nearest tenth unless they tell us to do otherwise, so be careful with that here. If you have any questions, please feel free to reach out via email, and I'll be happy to assist. Have a great day. Oh, before you go, we also have one final bit here that might be helpful when it comes to talking about your test. So I did want to tack this onto the end here. This is this final slide of these notes. Notice whenever you've got this cylindrical tube of popcorn versus the cone shape of popcorn, volume-wise, this guy is 1/3 of this guy, right? So kind of keep that in mind. That is a hint for you for your upcoming test, that you may need to be able to draw that conclusion between one of them being 1/3 of the other. And then there may be a question kind of like this one that just says, hey, which of these is a better deal? So kind of think through that. If you look at this, since it's 1/3 of the other shape, we would be able to guess that the price of the big tub should be 3 times as much. However, since it's only double, better deal-wise, the cylindrical tube is our better option, because it's not as expensive as it would be to buy 3 of those little cones, which would be the same amount of popcorn. Now you guys know I love popcorn, so I had to circle back to this question, but please make sure that you do look over this particular question and make sure you're comfortable before your test. Have a great day.